Welcome! Today, we're diving into the incredible evolution of supercomputing. It's a story that starts with machines filling entire rooms and powered by technology that seems ancient now. Vacuum tubes. Think back to the dawn of high-performance computing. Early systems like ENIAC, UNIVAC LARC, and the IBM 7030 Stretch in the late 50s and early 60s used vacuum tubes or very early transistors. These giants were groundbreaking but plagued by heat, unreliability, and massive power consumption. Their main jobs: complex calculations for military and atomic energy research, tasks impossible before. The real game changer arrived with the transistor. Smaller, faster, more reliable, and way more energy efficient than vacuum tubes, transistors paved the way for genuinely powerful computers. This is where Seymour Cray enters the picture. Working at Control Data Corporation, he led the development of the CDC 6600, released in 1964. Many consider this the first true supercomputer. It used silicon transistors and clever design, including early forms of parallelism, blowing past the performance of its rivals. Next came integrated circuits, packing even more power into smaller spaces. Seymour Cray, now heading his own company, Cray Research, unveiled the Cray-1 in 1976. It wasn't just famous for its unique C-shape that minimized wire lengths. It mastered vector processing. Instead of handling data one piece at a time like scalar processors, vector processors worked on whole arrays or vectors simultaneously. This was perfect for the repetitive calculations needed in weather forecasting, fluid dynamics, and engineering simulations, making Cray systems dominant for years. But the hunger for speed didn't stop. The focus shifted towards parallelism, using many processors together. While early experiments like ELIAC IV explored this in the 70s, the 1990s saw massively parallel processing, or MPP, truly take off. Systems began linking thousands of processors. A key development was the Beowulf cluster approach, using interconnected standard, off-the-shelf processors. This made high-performance computing more affordable and accessible. Standard tools like the Message Passing Interface, or MPI, helped developers write software for these parallel machines. Then came another disruption: graphics processing units, or GPUs. Originally built for video games, developers realized their highly parallel architecture, hundreds or thousands of small cores working at once, was ideal for scientific calculations too. This GPU approach, often combining GPUs with traditional CPUs, provided massive speedups, especially for AI, machine learning, and molecular modeling. NVIDIA's CUDA programming model, launched in 2006, made GPUs much easier to use for science, accelerating their adoption, which brings us to today. The world's leading supercomputers are massively parallel beasts, often combining tens of thousands of multi-core CPUs with powerful GPUs, all linked by incredibly fast networks. We measure their speed in petaflops, quadrillions of calculations per second, and now, exaflops, quintillions per second. Systems like Frontier, Aurora, and El Capitan are at this exascale frontier, tackling immense challenges in climate science, drug discovery, materials science, and fundamental physics. Of course, challenges like huge power consumption and heat management persist, driving innovation in cooling and energy efficiency. The journey of supercomputing is far from over. It's a continuous push, expanding the boundaries of what's computationally possible and opening doors to new discoveries. Thanks for tuning in.